Alright, we're now on part 2 of our astronomy notes, and what we're going to look at today is stars and star color and how stars are formed. And the first thing we look at in your notes is that how do they know about the distance of stars? First off, they use what is called a parallax, and we'll get into that a little bit further down the road as we get going. But then we look at star color. You know, star color indicates the surface temperature. Red has a longer wavelength than blue, so it is cooler. And then stars are classified by their temperatures. Right here we have a spectrograph that is showing the elemental changes on the spectrograph. And this is how we classify the stars. Next thing we look at is what are the hottest stars and what are the coolest stars. Well, obviously if you're looking at the different colors, you're going to look at the fact that we are looking, if blue is the shorter wavelength, so therefore it is going to be the hottest. White would come next, then it goes to the yellow, which our sun is to that stage in the middle there. Then you have the red, and then eventually the brown being the coolest. Then we look at magnitude. Magnitude means brightness. Now, there are two types of magnitude that we deal with in astronomy. The first is the apparent magnitude. And the apparent magnitude is how bright a star appears. Now, if we go outside and we take a look at different stars, sometimes we will see some stars that are brighter than others. As we look at this image here in the background, we can see that some of these stars here they look brighter than some of the ones that are a little further off. But that may not be the truth. They may not actually be brighter. But apparently, and that's why it's called apparent magnitude, apparently it looks like it's that bright. So again, what is the most apparent star that we see? And that would be the sun, because it is closest to us, so therefore apparently it looks brighter than all other stars. Then we get to the second one, absolute magnitude. And absolute magnitude is the actual brightness of a star. And this is if we take all the stars and put them at the same distance away from us, and we were able to look at them, this is going to show which one is actually brighter. You know, our sun is a medium mass star, so therefore it's not really as bright as many of the others that are out there in space. But the interesting thing about it is, because it's closer to us, we feel that it is very, very bright, and we can't really understand of how another star could be brighter. But when you take into account of a distance, you can start realizing that that's the truth. And an example that we always try to use or take is, if I take a light bulb and turn it on and put it right next to your face, obviously that looks a lot brighter. But then I take that same bulb and I take that a mile away, it doesn't look as bright as it was right next to your face. Again, absolute magnitude is if all were the same distance away. Now, getting back to that first question we asked is, how do we know how the distance of stars? Well, we use a mathematical equation called parallax. Parallax is a star's apparent shift in its position. You know, parallax can be used to determine the actual distance to a star by our change in our position. If we take a look over here at this image, we can see that where we're at, according to our Earth in January on this side over here, we can draw a straight line to an apparent position of a star location here, and then as it rotates around to Earth in July, we can also create another triangle using the sun as our center point, and we're able to take this angle right here called the parallax, and that is going to give us that in many cases the Pythagorean theorem and a mathematical equation that gives us the distance. And yes, we do use math in science, especially in astronomy. Now we look at the life cycle of a star. In order to understand the life cycle of a star, the first thing you got to understand is how does the star build? If we look over here, we have the star formation, and this star formation is what we're going to call the nebula. Again, in the nebula we have gas and dust. It is all going to start collecting, and as it builds and builds and builds and builds and builds, as we see the dust pattern over here, it starts to create more gravity. And again, we said the more gravity, or the more mass, the more gravity we have. So the more gravity we have, now we start to condense things down, and it pulls that gas and that dust in. And as that pulls all those things in, it gets to a point where the mass is so great that there's a spark. And we'll talk about where that spark comes from later on. But then there's that spark. Then the star forms in that sudden instance of that spark. And at first thing, the star becomes this protostar. I equate it to what happens when you take a fire, and maybe you're getting ready to start the fire and you douse it with lighter fluid. Well, what initially happens when you start it? Well, you get that huge ball of fire at first, and that would be considered what's called your protostar. Now your protostar would be your first initial star right here in the center, right there. And then as we get going through here, we have what's called the sun kind of gets into this point where it starts burning that first gas, that hydrogen and helium, and it becomes this main sequence star. Now after the main sequence star, depending on the size of the star, it goes into its different stages. If it's a low mass star, and again that's a low mass star because we have three types. We have three types of stars that we technically classify. You have called the low mass star, you have the medium mass star, and then you have the high mass star. Each one has a different lifespan. The low mass star goes from the protostar to the main sequence. From the main sequence, it dwindles to what's called a white dwarf, and then eventually kind of stays in that state for a very long time. The low mass star actually, this one here, the low mass star, is actually your smallest star, but it also lives the longest. It can live easily billions of years, and it is probably the one that is going to sustain the best throughout time. Then you have what's called your medium mass star, and our sun is a medium mass star. It's not a high mass star. So the first thing you know right away is that it will not blow up. You look at the medium mass star, and the medium mass star will move to the red giant stage. So yes, as you're looking here at this picture, our star will become this red giant stage, probably in this vicinity, because this is kind of depicting the supergiant right here. But ours will become a red giant. And in many instances, scientists and astronomers believe that when our sun becomes a red giant stage, it'll reach outwards to about the Earth's orbit in size. Then after the red giant stage, what it ends up going into, not a supernova, but what is called a planetary nebula, and this is where the star itself will become very volatile, and it'll start just throwing off shells of the additional gases that are left behind, and then this will start to dwindle down to where it'll become what's called a white dwarf, again down into this stage, and then eventually the black dwarf, which is the dead star. Then we go to the high mass star. The high mass star lives the shortest. We're talking millions of years, not billions of years, millions of years, which is a huge difference between the 100 billions to 10 billions that the medium mass star, and then now we're into millions. Very, very quick. It starts here in the beginning stage of the nebula. The nebula is large enough, and the mass is great enough. This can become a high mass star. When the spark happens, what it does is it will actually trigger this event and quickly go into the main sequence. Then the main sequence will quickly go into what's called the supergiant, which is magnified enormous. And as it gets so large, the pressure and the gravity is so great that it can't keep this thing together anymore, that it starts triggering a massive explosion. And probably the greatest explosion in the universe that we can even imagine is called a supernova. And the supernova means super new, nova meaning new. And this explosion sends all these elemental plasmas and particles and dust and gas all out throughout the reaches of space. Now, if the explosion is large enough, and if it doesn't fall down and in on itself, and this is a little complicated, but again, if the neutrons explode outward, it leaves a void, which is known, in many instances as a black hole. And a black hole is essentially a hole that light cannot escape. The gravity is moving so fast that light cannot escape it. And then we also have what's called a neutron star. So if the neutrons don't escape and they fall in on themselves, what they'll become is a very, very super dense object known as the neutron star. Now that concludes our second part of Astronomy Notes, and hope you make sure you follow along on your note-taking sheets, and make sure that you've got these down and study for the test.